Okay, so in this video I'm going to go over the only C3 international paper that actually ever existed, because Edexcel then went to C3 and 4 papers combined. We used it in Havant Sixth Form College as a mock this January, and let's say it was mixed, the response to how it went down. Some very, very good ones and some people getting a bit mixed up. So this is an attempt to try and address that. Apologies to anyone from outside Havant Sixth Form College, because this is going to be a bit of a rant at times. Anyway, now the first bit is, most people could do this. It's numerical methods question. We need to know that sec x, of course, is 1 over cos x, which I think everyone did know. So that then makes it, all we have to do is put these numbers in a calculator to show there's a change of sign. So if we put f of 0.2 in, okay, that's 1 over cos 0.2 plus 3 0.2 minus 2. Now that comes to 0. Minus 0.4. Okay, and then f of 0.4 is 1 over cos 0.4 plus 3 times 0.4 minus 2, and that equals to 0.3. So that's less than 0. This is greater than 0. Now, this is actually a special case of something called the intermediate value theorem, which assumes continuity and various bits, but we're not really expecting a formal kind of response here like it were a first year analysis course at university. All we really need to say is that there's a change of sign, which implies that there exists a root in interval 0.2 to 0.4. I always think it's safer to actually refer back and write something to actually say that we've actually proven it. Okay, so that's that. Before I move on, I just say one thing about radians and degrees? It's radians anyway because of this. That's clear. It is a clear indication it's radians. In any case, it should be our default position that radians are what our units are for, and particularly anything which is kind of mixed in nature, where you've got an algebraic term and a trigonometric term. It will be radians. It should be, unless otherwise told, it will be in radians. So there were a number of people who used degrees, who also knew they were using degrees because they used the units in the calculator. So it wasn't a case of forgetting the mode, to change a mode on the calculator, knowing it was degrees, but forgetting to change a mode. It was actually a case of not realizing in certain instances that this should be in radians. Okay, so there's a little first rant. Anyway, part B. We need to get into the form x equals to gx, but this one hopefully we can see, because we've got the equation fx equals 0 is 1 over cos x plus 3x minus 2 equals 0, which gives us 3x is equal to 2 minus 1 over cos x, which if we divide by 3 is x is equal to 2/3 minus 1 over 3 cos x. There's only one mark, so we don't really want to make too much of a fuss of that. Okay, so that's the first part done. Part B, sorry, done. Now the next bit is just using this iterative procedure here, this formula. So to work out x naught, x0 is what's given. To work out x1, we just put into this formula. So that's 2/3 minus 1 over 3 cos 0.3. And that equals to 0.3177. And it does say 4 decimal places, so we better give 4 decimal places. And then what we do is we do the same procedure again. I won't write every single one out. But basically what we're doing is we're putting, instead of 0.3 in, we're putting 0.3177 in. And that's x2 equals to, x2 comes to 0.3158. And then again, we put that into the formula, that number then into the formula. X3 is not equal to that. X3 comes to, when you put that in, to 0.3160. Okay, so those are our four values that were, well, the first one given, and then the three others that need to be calculated. One thing I would say, most people do now seem to be able to use a calculator for this, but we don't have to write an expression like this 3 times. What we do is, if you use your calculator with an appropriate answer key and execute key or whatever, what you would probably type in your calculator is your first value, your x0, and just type equals or execute, depending on what your calculator says. So on calculator, don't write this, you don't need to write this in the exam, of course. On so you write in that, and then type 2/3 minus 1 over 3 cos answer. And then repeat, then repeat the equals execute to get successive approximations for x. And that will do it. And so you don't have to type this in with 3 different numbers, or even more sometimes. So that's something to get used to. I think most of the ones I marked were using that, I think. But it might be useful if you haven't seen that before, to make sure you know how to use your calculator. Okay, not quite finished yet. It says state the value of alpha to correct to 3 decimal places. So obviously this to 3 decimal places is 0.316. Okay, so nice easy first question. Let's have a look at second question. So when I saw this question, I thought this was going to be a nice straightforward question that everyone would be able to pick up 4 marks for. How wrong I was. Yeah, you'll see why in a moment. Basically, most people know how to put over a common denominator. Here we need to times this bit by x minus 1 on top and bottom. And then we times this bit by 3x plus 4 on top and bottom. So let's just write that out. 15 3x plus 4 times by x minus 1 over x minus 1. So that's that times by 2x minus 1 on top and bottom. Then 2x x minus 1 times by 3x plus 4 on top and bottom. And obviously the last term is unchanged because it's already got those factors on the bottom. Okay, so that's so we now have a common denominator. If I multiply out the top, 15x minus 15 minus 6x squared minus 8x plus 14, and that's all over common denominator of x minus 1, 3x plus 4. Okay, so that comes to minus 6x squared on top. Then we've got plus 7x. And then we've got minus 1. Now, here's the thing. Most people got that bit, okay, they put a common denominator, but they left it there. Now, most of the time, the examiners do it so that there's a common factor here that factorizes. So we should be looking to factorize this if we can. Almost to the extent to start these questions is, it obviously doesn't have to factorize mathematically, you know, it's not inevitable mathematically that it factorizes, but everyone I've seen on the exam does. So it's almost to the extent that if it doesn't, you should be wondering whether you've made a mistake before, rather than just leave it there. Or even worse, multiply out the bottom and use that to try and do the next bit and see in terms in x to the 4 and all kinds of stuff. Sorry, I'm a bit jaded. I've seen lots of very complicated algebra for this. Another little gem I saw was changing the top. This is wrong, by the way, so to this, as though you could just do that. I didn't like actually at least realised that this was probably going to factorise, but because I didn't like the negative here, chose to change the sign of everything. You can't do that. If it's obviously an equation like this, if you have minus x squared, if we had minus 6x squared minus 7x plus 1 equals 0, then of course, or minus 1 equals 0. Then of course we can change that to 6x squared plus 7x. I've got an incorrect sign there, but you get the idea. We can do that because of the equality with 0 here, because it's an equation. But we can't just change a negative quantity exactly to a positive quantity. That's just like saying 4 is equal to minus 4. Just rubbish. So I saw that about out of 50 scripts. I saw that about 8 or 9 times. So anyway, if we do that, then it's okay. Or stick a minus 1 thing. So then that's okay. So I understand the need to actually want to keep this so that we can factorize nicely. But we don't do incorrect mathematics just to do that. Anyway, so the top is minus. That factorizes, I think, we've got a 6x minus 1 and an x minus 1. That gives me x minus 1, 3x plus 1. So that factorizes. So we can write that now as minus 6x minus 1 over 3x plus 1. We can leave it like that, or you might prefer to get rid of the negative on top there. So it factorized and it's simplified, and now that's going to make it a lot easier to work with in part B. So those who didn't factorize not only lost the 2 marks on that, inevitably got a maximum of 1 on the next part. Okay, I'm just going to reduce this a bit and then do part B. So part B, now that we've got it nice and simplified, we can use the quotient rule, let u be equal to the top bit, which is 1 minus 6x, and v be equal to the bottom bit, which is 3x plus 1. du by dx is then equal to minus 6, and dv by dx is equal to 3. The quotient rule says this: dy by dx is equal to v du by dx minus u dv by dx all over v squared. So that comes to minus 6 times by 3x plus 1. Take away u, which is times by, so it's that times that, so it's 3 times 1 minus 6x all over 3x plus 1. Ooh, I seem to have changed that to a 1. It's obviously wrong. Obviously in a rush to get this done. It's a 4, it should be a 4 all the way through there. Nice easy one to change anyway. So now that comes to right, okay, so that comes to minus 18x plus 18x cancels on the top. We get minus 6 there, and that's squared there, so that's, oh no, of course there's a 4 there, which I've also missed out, so it's 3x plus 4, so it's minus 24 minus 3, so it's minus 27 over 3x plus 4 squared. So apologies for my own mistake after moaning about other people's mistakes there. Okay, I think apologies if you had something, we had a break there or something happened with my computer. I don't really want to start again, so I'm going to carry on. There was also a mistake of a 4, I mysteriously changed to a 1. I was moaning about students' mistakes, and then just did that because I just want to rush through this and get as much done as possible. But anyway, that is now the correct answer, and my point about cancelling still stands. Okay, let's get on with question 3. Okay, so a trig and differentiating thing. Right, first part, we're using the chain rule. You can use the quotient rule, but it's not particularly, we prefer the chain rule really. Now the chain rule basically says if we write it, we can write it in various forms, but we can write it, if we have a function with inside a function, say this, if we're differentiating it, then we can just differentiate what the function is. But to adjust for the fact that there's a function inside it, we'd have an f stroke x there in front. Okay. So that's, or sometimes we might write it the other way around with g and f swapped. It doesn't matter. I might have previously written it like this. But anyway, the point still stands. G stroke x and f stroke of gx. Now, if it's inside a power function, for example, d by dx of some fx to the power of n, that will be a normal rule for differentiating differentiating a power is to times by the power and then take 1 off the power. But to adjust for that, it's f stroke x in front. So that's the chain rule, the particular case of the chain rule, where we have the function of something else, which is what we've got here effectively, because if I'm finding d by dx of 1 over sine x, that's the same as d sine minus 1 x. Let's write it like this to, okay, avoid any confusion with the arc sign. And then so we're going to have minus 1 sine x to the minus 2, but then we need to differentiate that sine x in front. So we have that. Now that equals to minus cos x. Now sine x squared is, sine x to minus 2 is sine squared x. I'll change it back to that now. But we want to get here. So what we need to do is split, and you should notice that we've got sine squared on the bottom, and that's going to come out if we split the sine squared into the sine x times by the sine x. So we split it into this, minus 1 over sine x, 1 over, not 1, cos x over sine x, which is equal to minus cosec x cot x as required. Okay, so that's how we do that pretty much. Now, some people don't like writing this with the d by dx. It's okay to just say let y equal 1 over sine x and use the conventional the chain rule as written like this if you want. Doesn't matter. it's trying to cut down on writing really. Okay, so that's part A. Part B, well, this is a product rule really, although some people did use the quotient rule by calling cosec x as 1 over sine 2x, but it did suggest from the first part that we're going to use the expression we had before. So we've got y equals e to the 3x cosec 2x. So if we let u be equal to e to the 3x and v equal to cosec 2x, du by the x is 3. That's basically a very simple case of the chain rule. And dv by dx, this is where, mistake alert, a lot of people missed out this 2 there because it's cosec 2x. Almost just pulled down the thing above and completely and forgot that the actual 2 would actually have an effect. So that's that. Yeah, basically this is using the product rule with that times that plus that times that. I'll write it out. Product rule dy by dx equals to u dv by dx plus v du by dx. Okay, so we're using that. So that gives us dy by dx is equal to minus 2. I'm just doing this bit now. E to the 3x times cosec 2x cot 2x, and then I've got plus 3e to the 3x cosec 2x. Now, I think that's simple enough. Yes, cosec x can be taken out as a factor and e to the 3x can be taken out as a factor, which will be useful in the next bit, so I'll do that anyway. But that actually got the 3 marks that were necessary for this. So that gives us e to the 3x cosec 2x times by, let's swap these 2 around, then 3 minus 2 cot 2x, slightly simplified. Okay, let's have a look at the last part. Now the last part, as I said, you didn't need to simplify for this part, but in fact it's useful to have this expression to equate to 0 now. So it's a turning point, it gives us dy by dx equals to 0. So you have e to the 3x cosec 2x times 3 minus 2 cot x equals 0. Now this can't be 0. E to the 3x is always greater than 0 and cosec 2x is never equal to 0. So we're basically, this reduces it to 3 minus 2 cot x equals 0. So we have 2 cot x is equal to 3, or cot x, making a bit of a meal of this, is 3 over 2. So there's a 2 again, I'm rushing this obviously too much. There's a 2 there as well. Yeah, dear. Okay. It's all going wrong, the phone going as well. Anyway, this is pretty routine stuff now, I think. Anyway, cot 2x is equal to 3 over 2. I'm making a bit of a meal of it anyway. And then we can say that tan 2x is equal to 2/3. So that gives us that 2x is equal to arctan 2/3. So x is equal to half arctan 2/3. So k equals 2/3. They've asked us to state it. There you go. Okay, so that is part C. Okay, I probably need to slow down a bit so I don't make these little errors where I'm just trying to get through as much as we possibly can. Okay, so let's have a look at question 4. Okay, so this is a nice exponential and log question. Done pretty well by most people actually. The first part's a 1 mark question, so it's not going to be too much involved. You could basically it wants to use the fact that at the start it's 85 degrees. Okay, so when t equals to 0, we got it as 85 here. Well, we got when t equals to 0, this is equal to 1 here. So in order for it to be 85, that will need to be 25. Be careful, but you don't really need to write any work in there. A is 25 is the answer there. So when t equals 0, A equals to 25. T equals to 0, theta equals 85, so that gives A equals 25. Okay, part B, here we're using the 15 minutes at 58 degrees C information. So we're going to have 58 is equal to 25 plus 60 e to the minus kt, and we know that t is 15. So we can take that away. So we've got 60 e to the minus 15k is equal to 33. So e to the minus 15k is equal to 33 over 60. And if we divide that by 3, that becomes 11 over 20. I'm now going to swap that over, because that's 1 over e to the, there is 1 over e to the 15k. So if we flip it over, we get e to the 15k is equal to 20 over 11, which is kind of where we're heading, isn't it? So it's not, we're being asked to show for it, so it's as long as we show each step carefully, we're fine. Now we can just say undo the e by lunning both sides, or lunning it, so it gives 15k is equal to ln 20 over 11, so it gives me k is equal to 1 over 15 ln 20 over 11. Now that amount evaluated is 0.039855 and various stuff, which I've stored on my calculator. But you won't get, if we don't see what you've been asked to say, you won't get full marks up. I've stored it on the calculator, which basically means I don't have to, I can still write k in my working for the next bit to, without knowing that I actually know k. You'll see what I mean. It says, find the temperature it reaches at 50 degrees C. So we've got 50 is equal to 25 plus 60 e to the minus k times t, big T, okay, for the time it takes, a particular time when it's 50. I'm not going to bother writing this value of k every time, or even write the number 0.0398 until the end, just to save a bit of writing, make it look a bit neater, because we know k, okay, and we can just do the manipulation, the calculation at the end. So we've got 25 is equal to 60 e to the minus kt. So we have e to the minus kt is equal to 25 over 60. Divide that by 5, which becomes to 5 over 12. So I can do a similar thing, kind of reversing thing to what I did here. So that gives me e to the kt is equal to 12 over 15. Not over 15, 12 over 5. So I've now got kt is equal to ln 12 over 5. So k t is equal to ln 12 over 5. I know what my k is now. I know it's this. 1 over 15 ln 20 over 11. And if I work all of that out, that gives me to 21.96 or 22 minutes. It's after 11 a.m. They weren't expecting, but just in case they want the time of day, it's 11:22. So moving on to question 5 of the C3 paper, it's January 14 International from Edexcel. Here we've got a curve expressed in the way x is a function of y rather than the other way around, which is more usual. So that caused a bit of difficulty. First bit's a pretty standard R formula thing, but I think the swapping of x and y did confuse a few people. What we're basically doing is writing R, let's do it this way around, 3 sine y plus 3 cos y in the form R sine x plus alpha. So there's particular values of r and alpha which makes this algebraically identical to this. Okay, so what I'm going to do is use the compound or addition formula on the right hand side here. So we've got r sine y cos alpha plus r cos y sine alpha. And that gives me r cos alpha sine y plus r sine alpha. I'm just reversing the trig ratios. You'll see why in a sec. Okay, so that means that I can compare the coefficients of these things. So I can compare coefficients. Now, for those of you who may be thinking I'm making a meal of this, or you might even be drawing a triangle or other things, or just saying that r squared is equal to 3 squared plus 3 squared, that's fine. I'm just perhaps doing this one a bit of a slightly longer way, just to kind of justify what's going on. So we're comparing coefficients, which basically means that any term in sine y, if these are identical, the terms in sine y have to be the same. So we've got 3 is the same as r cos alpha. And we've also got this 3 is the same as r sine alpha. Okay. So let's just write that out. R cos alpha equals 3 and r sine alpha equals 3. So the normal thing to do is divide the two here. If you divide these two, you'll end up with sine alpha over cos alpha, which is tan alpha, equals 3 over 3, which is 1. So alpha, and again we're in radians here. We should be in radians most of the time. I mean, we're differentiated in the next part, which basically means radians. But as I said in an earlier question, the fact we almost, even if that, in the absence of that, we would be assuming radians. It's our default position with algebra and things at this level. And, you know, it'll always be clear if it's in degrees. Anyway, alpha is equal to pi by 4. And then I can square and add these. You end up with sine squared plus cos squared equals 1. But basically that gives us r squared is equal to 3 squared plus 3 squared. So that gives me r is equal to 3 the square root of 2, or the square root of 18. Okay, so that's the first bit. I probably ought to go back. I think we've probably done enough to get the marks, but just to be safe, probably ought to write out our formula here with the values of r and alpha that we found. So it means that is algebraically equivalent to that. And we're going to use it in the next part. Okay, so now the next part is using differentiation. Okay, now what we really need to take care of here is the fact that the variables have been swapped around. The fact that we've been asked to do this probably means that this formula is going to be more useful than this one. So this kind of common thing they do. So this formula is the one we're going to use to find dy by dx. But we've now got, so I've written y here, of course. We've now just see how it can be done where you get confused with symbols. So it gets so used to writing x that even there I wrote a y in. And I did it here as well. Well, or maybe I didn't mean to, but it looks like that should be a y there too. So anyway, we've now got our expression functions. X is equal to 3 the square root of 2 sine y plus pi by 4. And it's to do with a gradient, dy by dx, but it's easier, obviously, or what we really need to be doing is finding dx by dy, where the symbols are changed around like that. Now, this is just going to be that. There's no number in front here, so there's nothing we have to multiply by. And it's just a straight swap for sine for cos when we differentiate sine. So that's dx by dy, but we being said the gradient is a half. So I suppose we could write dy by dx is equal to 1 over that. Pi by 4. But we're actually told that that's equal to a half, which must mean that this is equal to this. So we have 3 the square root of 2 cos y plus pi by 4 equals to a half. Oh, not equals to half, equals to 2. So now it's just a case of solving that equation. Dividing through to make it just a number on the right hand side. That's 2 over 3 the square root of 2, which is actually equal to the square root of 2 over 3. Now if I find the inverse cos of that, I'm going to get y plus pi over 4 equals to 1.0799 and a whole lot of other stuff. Now, normally, obviously, that might not be the only solution, but I've got a very restricted range with what y is here. So if I add 2 pi to this, for example, I'm going to be way out of our range for y, even after taking pi by 4 off. And also, if I take the negative of that and take pi by 4 away, I'm going to be off it. So that's the only solution that I need to consider. There are other ones, but in this range, that's the only one that's actually going to be valid. So that gives me y equals to minus pi over 4. So that gives me 0.295 to 3 significant figures for y. Now, don't forget it wants the coordinates. So we need to go back and put that in terms of the x coordinate. Okay, I've got it stored on my calculator. Just put the number in the calculator and put it back into there, your 0.95 into there. And if you do that to 3 decimal places, you're going to get 3.742, I think. Yeah, if you use the more precise answer, I think if you put 0.295 in, you get 3.743, which is actually wrong to 3 decimal places. They were generous on this and they accepted it on the mark scheme, but that's the more precise answer. Okay, so now let's look at question 6. Okay, so the first bit's a nice sketching thing. I'm going to just imagine the modular sign isn't there, then it's just something with gradient 2x but intercept a. So it does this. Okay. And it would go through, because it's got gradient of 2, it would go through a here, but it would go through minus a over 2 here, because it equates to when y equals to 0, so that occurs when x is equal to minus a over 2. But this bit here obviously gets modulated, so any negative answers get changed to positive. So that actually comes there. Like that. So that's the first one, a couple of marks for that. The 4 marks are for the next bit. Now this is obviously the same graph here but shifted downwards by minus b. It does tell us that b is positive, so that means it's shifted downwards and that it's greater than a. The significance of that means that this must pass further down than the origin, because we know that b is greater than a, so it can't go through the origin and neither can it go above the origin. So we're going to have the sketch. That's not very straight. That's not very straight either, but probably be all day if I do that. So it's not going to be going through the origin. It's not going to go like that either, because we know, it's not going to go through the origin like that, I mean, because we know that b is greater than a, and neither is it going to do that, because we know that b is greater than a. So it's gone down by b. So we know it's gone further down than b, and it wants all the coordinates where it crosses. Right, well, this coordinate's probably the easiest one, because it's gone down by b. So this must go through a minus b, which we know is negative, because of this. Keep coming back to that. Right, now to find this coordinate, if we use the fact that the y coordinate is equal to 0, this part of the graph here is basically the same as 2x plus a, or y equals to 2x plus a minus b. So that part of the graph is that, and we want when that is equal to 0. Okay, so rearranging that gives me the coordinate x is equal to b minus a over 2. Okay, now if I consider this part of the graph here, so we want to find where the coordinate crosses here, this one here. Well, that part of the graph is exactly when we've got minus 2x plus a minus b equals to 0. Okay, and rearranging that, I get minus bracket a plus b over 2. Okay, so a little bit fiddly, but that's it, 6 marks for that. And then the next part, similar kind of thing really. It wants us to solve the equation where this graph crosses the graph of third x, so basically where it crosses here. So we're going to have 2 points, one here and one here. So one's going to correspond to the positive part of that, so 2x plus a will be, and then the other one, similar to what we did here, we'll consider the negative part of that to solve the 2 bits. So first of all, to get one of them, let's change back to, we get for the one that was up here, the positive one, that's 2x plus a minus b is equal to a third x. So taking everything over, we get 2x minus a third x is equal to b minus a. So that's 5 over 3x equals b minus a. So x equals 3/5 of b minus a. And then also, as I said, we also need to consider the negative part of that, so which corresponds to the intersection with this part of the graph, which is minus 2x plus a that bit. So we've also got minus 2x plus a minus b is equal to a third x. So we have minus 2x minus a minus b equals to a third x. Taking everything over to the one side there, we get 2x plus a third x equals to minus a plus b. Rearranging a bit, so that gives me 7 over 3x is equal to minus a plus b, which finally gives me the solution x is equal to minus 3/7 a plus b. Okay, so reasonably fiddly, but it's not too bad. A couple of questions to go. Let's have a look at question 7. Okay, so this is a trigonometry question. Part A is, well, there's no excuse for not getting this. This is what we always used to call standard bookwork. There won't be a textbook, I don't think, out there that doesn't show you how to deal with triple angles. And they've even given the formula here. You don't have to refer to the formula book. The reason is that is not really to give you the hint. It's because I think they're worried that the really studious and will actually attempt to prove that, which it is provable, but that's not what they're asking to do. And if they did, they would give them a lot more than 4 marks for it. So I think that's why they put that there, because they were worried that some students might have actually thought that this was something that needed to be proved, which it can be, but it's certainly what they're asking for. So first of all, what we're going to do is call cos 3 theta equal to cos 2 theta plus theta. Now, using this compound angle formula that they've given us, cos 2 theta cos theta minus sine 2 theta sine theta. Right, now save yourself the trouble. Now it's free formula, you might know. Our starting point with cos 2 theta is cos squared theta minus sine squared theta. But if you use the Pythagorean identity, sine squared plus cos squared equals 1, they can be converted to 2 cos squared theta minus 1 or 2 sine squared theta minus 1. You really need to know these. I know some say, I'm going to go back to that. The trouble is that life is going to be too slow. We really need to know this, or at least this, and know of these, and that we could get them quickly in the margin or whatever. I did see some people substituting not the easiest formula here. This is the one we want because we want it in terms of cos theta. Yes, of course we can get there using the other ones, but it's slower. And if you get it wrong, you're less likely to pick up the method mark. So anyway, let's replace that with 2 cos squared theta minus 1 cos theta. Okay, and then this bit, we know the formula for sine theta, 2 theta. We should know 2 sine theta cos theta, but we've already got a sine theta there. Okay, so let's multiply that out. We get 2 cos cubed theta minus cos theta minus 2 sine squared theta cos theta. Okay, maybe save a bit of time here and put 1 minus cos squared theta there, because we want it entirely in terms of cos theta. So that comes to, well, we know what we want to prove, and I think, well, let's just do one more line just in case. I was just going to write the answer there, which I think would probably be okay, but there we go. Okay, done. I say standard bookwork, absolutely no excuse for not knowing how to do that. Okay, part B. We've got a trig equation here, and it says hence, so we haven't even got a choice here, but how else we'd want to do it, I don't know. We've got that formula for cos theta. We also know a formula for cos 2 theta here. So let's just put all that in. 2 times 4 cos cubed theta minus 3 cos theta plus cos 2 theta. Remember, it's easier we want it all in terms of cos squared, so it's 2 cos squared theta minus 1 plus 1 equals 0. These cancel quite nicely. So I end up with 8 cos cubed theta minus 6 cos theta, but I'm going to end up with plus 2 cos squared theta, and then minus 6 cos theta equals 0. Now, a really annoying error I saw here was for people to divide by cos theta. And although you get some of the solutions, you lose solutions if you divide by an algebraic term, or you could lose solutions. Dividing by 2 here is no problem, because 2 is not an algebraic term and it's not equal to 0, so that's fine. So we can easily call out 4 cos cubed theta plus cos squared theta minus 3 cos theta. No problem with that, but there is a problem with this, unless you realise that you actually eliminating a solution this way. There is a problem with this, unless minus 3 equals 0. That is a problem, because we have neglected the cos theta term, which itself can be equal to 0. So we can factorise that inside. It's right now, I'm just saying if I left that out, which is what I saw from a lot of people, thereby losing a mark. It was only 1 mark in this case, I think, for one solution. So divided by a number, if it's an equation, is fine, as long as it's not divided by 0, of course, but divided by an algebraic term, which could be 0, is not fine. So anyway, let's just factorise this 4 cos theta minus 3, and I also get cos theta plus 1 equals 0. So I've got my 3 bits. Cos theta equals 0, 4 cos theta let's write it all out, so we can do that. Cos theta equals 3/4, or cos theta equals minus 1. Now, we're in radians still, so we must make sure that we've still got radians. In fact, degrees weren't involved in any of the questions on this paper. The range that we're doing is 0 to pi, so looking at this, there's only going to be one solution to that between 0 and pi, and there's only one solution between 0 and pi there for all of them. So we don't have to consider, we're just going to get one solution from each one of them here. This one, cos theta equals 0, gives us theta equals pi by 2. None of the other ones actually lie within the range. This one gives us theta, if I do arc cos of 3/4, I get 0.723. And don't write that, as a few people wrote that as a multiple of pi. You never write anything as a multiple of pi unless it's exactly a multiple of pi, and this one isn't. Okay, you can't write that as a multiple of pi justifiably. And this one here gives us theta equals to pi inverse cos. You can see that because the cos graph goes there. We've got one solution where it's 0, and the other solution where it's pi, so it's pi by 2 0. So yeah, those are our 3 solutions, and say there are no others. In this particular example, from each of these 3 factors only generates one solution. Of course, in another question you might have to consider more solutions. Okay, let's make a bit of space, and I'll tackle probably the hardest part of this question, which is the second part 2. Okay, so there's a couple of ways of approaching this. I'm going to use trig identities. There's also, we can actually construct a triangle for it first of all, but we need to start off with this simple thing. Arcsine is inverse of sine. So on doing that, we get sine theta equals x. Okay, well, we can therefore say that cot theta is, we need to know the formula for that, is equal to cos theta over sine theta. Well, we know that sine theta equals x, so we need to replace cos theta. Well, I might write this separately actually. We know that because cos squared theta plus sine squared theta equals 1, we know that cos squared theta is equal to 1 minus sine squared theta, and cos theta is equal to the square root of 1 minus sine squared theta. Okay, we know that. You might say, well, why not the minus, which would be quite justifiable, but we're told that the angle is less than pi by 2, so that means it's not negative. So let me just take that away. So you wouldn't have to write that in the exam. We could actually just write this. That's equal to square root of 1 minus sine squared theta over sine theta. And because sine theta equals x, we can say that's equal to square root of 1 minus x squared over x as required. Okay, the other way of doing this, which is also quite nice, is to move this out of the way. The other way of doing this is to construct a triangle from sine theta equals to 1. If I now mark using that a diagram with, and call that x over 1. So we've got sine theta equals to x over 1, opposite over hypotenuse, and mark a length there as 1 and the length there as x. I can say that this is 1 minus x squared using Pythagoras' theorem. I don't have to do this, by the way, I don't do both of these, so that's alternative. So we've got sine theta is equal to 1 over x square root of 1 minus x squared. So then we can just say tan theta, which is opposite over adjacent, and of course we're okay with SOHCAHTOA and normal triangles here because we know we're just dealing with 0 to pi by 2. So we have tan theta is equal to x over 1 minus x squared square root of x squared, which means that cot theta is equal to square root of 1 minus x squared over x. It's also quite a nice way of doing it. Either is fine. Okay, 3 marks. Not many people got it actually from our students anyway. So let's have a look at the final question. We're nearly there now. So they've left it to the end for the functions question. It's functions and logs and EX, so it's a bit of a mixture of things. Right, now first of all, the thing that strikes me is the domain here. It's worth knowing what this function looks like. If we've got some idea what this function looks like, it actually would be going through 3 here. It would have an asymptote to 3, should I say, and when x is equal to 0, we'd have 1 here, and it would do something like this. So the range of this function would be fx is less than 3, which will be the domain that they're asking for in the next part when we do that. Anyway, that's not strictly necessary, but it's quite good to look at things from a different angle so that we can get the question, because most people missed out on the domain, or they just wrote that x is not equal to 3, which is incorrect. So, so even people who knew what they're doing often made a mistake with the domain. Anyway, the standard thing to do here, I would say, is to write y equals to the 3 minus 2 e to the minus x. That's the function. So the inverse of that function, you're just swapping x and y around. So now we just need to get y the subject to the formula. So we've got, let's bring 2e to the minus y is equal to 3 minus x. So e to the minus y is equal to 3 minus x over 2. And I'm feeling a bit deja vu here, because I did see in an earlier question there was some logs and things. I swapped over before I even did the logs, because e to the y is just 1, e to the minus y is just 1 over e to the y. So I can just change that to positive and flip this around. So that just gives me y equals ln of 2 3 minus x. Let's write the inverse in the notation that we're normally. So that gives us, in the domain, as we said earlier, we can see it from the function here. X cannot, that bit on we can't put a negative into a log. So we can see it from that point of view. X has got to be less than 3, but we can see it from the range of the original function as well. Okay, so that's part A, 5 marks. Okay. Part B. It says solve the function f minus 1 equals to ln x. Okay. So let's just do that then. This is ln x is equal to ln of 2 3 minus x. Now, if these two are equal to each other, then of course the only way that can happen, because ln is a one-to-one function, the only way that can happen is this is equal to this. That wouldn't happen if the function, you couldn't deduce that in functions that are not one-to-one. For example, if you had sine x equals sine y, you can't say that x equals y, because, for example, x could be 0 there and y could be equal to pi. That doesn't follow. But if it's one-to-one, we can say that this will be not only a solution, it will be the only solutions. Okay, so that just comes to a quadratic. 3x minus x squared equals 2. X squared minus 3x plus 2 equals 0. So solving that or factorising. Nice to do a bit of factorising, a few easy marks this late in the paper. Of course, a lot of these things are just getting known what to do. Once you know what to do, what you have to do is not always that difficult. Right, and part C also, I would say, follows that pattern as well. Not many correct answers to part C, unfortunately. Okay, right, we've got original function, if we remember, we might have forgotten what it is. I suppose changing f to t, fx, we were told is equal to 3 minus 2 e to the minus x. So it also means that ft is equal to 3 minus 2 e to the minus t. We just changed the kind of letter of the variable. So we've got that. And we're asked to solve when it's equal to k e to the t. Okay, so we've got that equals to k to the t. So let's write out the equation. 3 minus 2 e to the minus t equals k e to the t. Now this is a quadratic type thing we see where we got the negative power. So if we times when we multiply out by the negative, it all works out because we've got this. So if we times by e to the t, we get 3 e to the t minus 2 is equal to k e to the 2t, but I'm going to write it like that. It's e to the 2t, but it actually makes it see what we're going to do easier here. Minus 3 e to the t minus 2 equals 0. Now it says, is that exactly one solution? So this must have one solution. Again, e to the t, if we let x equal to e to the t, or y equal e to the t, we get ky squared. And again, the e function, for those who are worried about it, is 1-to-1 as well. So there's no confusion about that. So if that's only, so if this has only got one solution, so has this only got one solution, because, as I say, e to t is 1-to-1. So this is a discriminant. Okay, so that means that b squared minus 4ac, so discriminant equals 0, equals 0. Okay, if I just rearrange that, there's plus 2 there. About that. Okay, so we've got this discriminant b squared minus 4ac equals 0. So that gives me minus 3 squared. So that's minus 3 squared minus 4 times by a, which is k, times by 2 equals 0. So that gives me 9 minus 8k equals 0. So k is equal to 9/8. So that's it. The final question of that paper caught quite a few people out. I think a lot of people weren't expecting it to be to do with discriminants. So a lot of people were getting this far and the like, but just didn't quite know where to go this late in the paper. The boundaries were relatively low, 58 for an A and I think 65 for an A star, 51 for a B, so perhaps the paper wasn't as easy as all that, but I thought it was actually, having gone through it, quite doable. Anyway, I hope you found this video useful, and sorry for the non-havant sixth form college students who might have to put up with my ranting, or even for some of the haven't sixth form college students who've had to put up with it too. Hope it's been useful anyway. Thank you. Bye.